Welcome dear learners. We are continuing Unit 4 Fundamentals of Analytical Chemistry. In the present module, we are discussing Permanganometry. The contents of this module are redox titrations, KMnO4 or potassium permanganate as oxidizing agent, permanganometry, selected permanganometric titrations, equivalent weight and calculations, concept of autocatalysis and problems based on these concepts. First of all, redox titrations. You are very much familiar with the volumetric analysis. In volumetric analysis, we are finding out the concentration of an analyte by measuring the volume. Volumetric analysis belongs to quantitative chemical analysis. In volumetric analysis, there are different kind of titrations like acid-base titration, redox titration, precipitation titration, etc. In this part of the discussion, we are first looking onto redox titrations. You are familiar with redox reactions. What are redox reactions? Redox reactions are the reactions in which there occur simultaneous oxidation and reduction. And the volumetric analysis, which deals with such kind of redox titrations or redox reactions, belongs to the category of redox titrations. Now, redox titrations are a type of volumetric analysis that rely on oxidation reduction reactions between the analyte and the titrant. In volumetric analysis, there is one analyte and there is another reagent called titrant. If there occurs some redox reaction between an analyte and a titrant, you can call that titration or reaction as redox titration. These type of titrations are used to determine the concentration of a reducing or oxidizing agent in a solution. Now, oxidation is the process which indicate or which is simply the loss of electrons, and as a result of the loss of electrons, there occur an increase in oxidation state. For example, suppose you are having a sodium atom. If it loses one electron and just converted to Na plus ion, then as a result of this process, the oxidation state of sodium increases from 0 to plus 1. That process is the loss of electron, at the same time increase in oxidation state. Such a process can be considered as oxidation. This I am just mentioning for the sake of a revision, so that you can easily understand the further concepts. Now, reduction. Reduction is just an opposite process of oxidation. Reduction is the process of gain of electrons. As a result of that, there do occur a decrease in oxidation state. For example, if you are having a chlorine atom and it attaches an electron and just converted to Cl minus. As a result of that transformation, chlorine from the 0 oxidation state changed to -1 oxidation state. That is gaining of electron, at the same time decrease in oxidation state. Such reaction is called a reduction reaction. Then a redox reaction is a reaction where these two type of reaction, that is oxidation and reduction, occurs simultaneously. That is, a redox reaction involves both oxidation and reduction simultaneously. Now, in redox titration, there must be a titrant, and in volumetric analysis, a titrant is a solution of known concentration, usually an oxidizing agent or oxidizing agent when we deal with the redox titration. In redox titration, there must be another species that is called the analyte. And analyte is simply the substance being analyzed. That means we are going to find out the exact concentration of an analyte or the species of which the concentration to be evaluated is taken as the analyte. So, there should be a titrant and an analyte. Now, in redox titration, certain cases we have to deal with some indicators. You are familiar with the indicators. These are a class of reagent used to find out the end point of a reaction. But as far as the redox reactions are concerned, indicator often not needed if reagents are strongly colored. For example, if you are dealing with some potassium permanganate titration, it is as such associated with some deep purple color. In that situation, we need not use any indicator to find out the end point of a reaction. However, in certain cases, external or internal indicators are used, and this is applicable for titrations involving iodine. In that situation, we are using starch as the indicator. The indicators, external indicator, internal indicator, etc., that concept we will discuss more thoroughly when we will discuss the situation of potassium dichromate or dichromatic titration. Now, how to find out the end point of a redox titration, or what is meant by end point? And end point is the theoretical point where the reaction appears to be stopped or appears to be completed. End point is the indication of equivalent point. Equivalent point is actual point where the reaction between the titrant and analyte is completed. An indication of the equivalent point is nothing but the end point. And the end point in redox titration is detected by a sharp color change due to the titrant or an indicator. For example, if you are dealing with some permanganometric titration, initially this solution appears to be colorless, and when the reaction is completed, we will reach the equivalent point, and the indication of the equivalent point is the end point, and that end point is identified by a color change. That color change is shown here. So, end point is can be identified by a sharp color change. Now, we can have some redox titration examples, and this chart will simply lead you through different kind of redox titrations which are very common as far as the volumetric analysis are concerned. The titration type, permanganometry. Here we are using potassium permanganate, which is an oxidizing agent, as the titrant, and the analyte may be Fe2+, that is the ferrous ion. It may be hydrogen peroxide, it may be some oxalate species like oxalic acid, etc. And the end point is from purple to colorless. And you are also heard about dichromate titrations. Here we are using potassium dichromate as an oxidizing agent, and the most important analyte is Fe2+ ion, that is the ferrous ion. Here we must have some indicator, and the indicator may be, the required indicator may be external or internal indicator. Another category of redox titration is iodometry, and here the titrant is iodine, and this iodine is maybe direct iodine or indirect iodine. That kind of direct and indirect iodine titration we will discuss in the coming modules. And here in iodometric titrations, you can have copper 2+, SO2, etc. as analyte, and in many cases iodometry titrations we are using starch as the indicator. The blue-black starch completely undergo decolorization, or there occur some decolorization, the blue color will disappear. That means these are some popular category of redox titrations. Now we are discussing potassium permanganate or KMnO4 as an oxidizing agent. Potassium permanganate, its molecular formula is KMnO4. Here the central atom manganese is in +7 oxidation state, and coming to its physical appearance, potassium permanganate is a purplish black crystalline solid that dissolves in water to give intensely pink or purple colored solution. This is the image showing solid potassium permanganate and a solution of potassium permanganate in water. Now, potassium permanganate is a purple colored material. As I just mentioned, it is associated with a melting point of 523 Kelvin. That is, it is thermally stable up to 523 Kelvin. Now, it is fairly soluble in water. The central atom manganese is in sp3 hybridized state as far as the hybridization of the central atom manganese is concerned. I already mentioned it is in the +7 oxidation state. At the same time, its hybridization is sp3 hybridization. Now, there are 4 oxygen atoms surrounded to manganese tetrahedrally as shown in this picture. That means here there is a central manganese. 4 oxygen atoms are surrounded around the central atom manganese. Since the central atom manganese exhibit sp3 hybridization, these 4 oxygen atoms are theoretically at the 4 corners of a regular tetrahedron, or this MnO4 minus radical permanganate ion exhibit tetrahedral geometry as well as tetrahedral shape. Now, potassium permanganate is a very powerful oxidizing agent in acid, neutral as well as in basic medium. So, in acid medium, in neutral medium as well as in basic medium, potassium permanganate can act as a powerful oxidizing agent. It is most powerful in acid medium. That means when you are mixing some potassium permanganate with acids like sulfuric acid, then you will get acidified KMnO4. Acidified KMnO4 is a very powerful oxidizing agent. Now, in acid medium, this is the reaction that responsible for the oxidizing tendency or oxidizing power of potassium permanganate. This reaction is the reaction between potassium permanganate and sulfuric acid. As a result of the reaction between 2 molecules of potassium permanganate with 3 molecules of sulfuric acid, you can see the products: potassium sulfate, MnSO4 or manganese sulfate, water molecule, and 5 nascent oxygen atoms are liberated during the titration. It is very well clear that these oxygen atoms are responsible for the oxidizing tendency of potassium permanganate. One more thing you have to note as far as this reaction is concerned, here in potassium permanganate, the central atom manganese is present in +7 oxidation state. And as a result of this reaction with the sulfuric acid, the +7 oxidation state of manganese is just converted to +2 state. That is, here occur some reduction. So, reduction happens to an oxidizing agent. That is, it is very well clear that potassium permanganate acts as an oxidizing agent as far as this reaction is concerned. Now, let us moving on to alkaline or neutral medium. In alkaline or fairly neutral medium, you can say that this type of reaction occur. That is, KMnO4 reacts with a water molecule to produce potassium hydroxide, MnO2 or manganese dioxide, and 3 nascent oxygen atoms are released during this reaction. So, in this reaction, here manganese is already present in +7 state, and this product is MnO2. In MnO2, manganese is present in +4 oxidation state. So, here from +7 to +4, this is also reduction. Reduction happens for an oxidizing agent. So, in this reaction also, potassium permanganate acts as an oxidizing agent. Whenever you are comparing these 2 reactions, it is very well clear that in the first reaction, that is in acid medium, there occur the liberation of 5 nascent oxygen. However, in the second case, the number of nascent oxygen liberated during this reaction will be 3. So, whenever you are comparing these 2, you can very well say that in the acid medium, potassium permanganate acts as most powerful oxidizing agent. Now, oxidation reactions of acidified KMnO4. You know that potassium permanganate in acidic medium is a powerful oxidizing agent. It can perform several oxidation reactions. Now we are looking on some important oxidation reactions of acidified KMnO4. First one, in acidic medium, you are familiar with this reaction, and the first reaction is acidified KMnO4 oxidizes ferrous sulfate to ferric sulfate, or simply Fe2 plus ions are oxidized to Fe3 plus ion. Fe2 plus ion is the ferrous ion, Fe3 plus ion is the ferric ion, and KMnO4, acidified KMnO4 can bring about this transformation from Fe2 plus to Fe3 plus as per this balanced equation. 2 ferrous sulfate plus H2SO4 and 1 nascent oxygen. Remember, in the above reaction, there occur the liberation of 5 nascent oxygen, out of which only 1 nascent oxygen is utilized in this case. You can balance this equation by incorporating or multiplying this expression with the 5, and you can couple this equation with the first equation. They are simply the theoretical procedures, but for the sake of easy understanding, you have to remember this equation. Here iron is present in +2 state, that is ferrous sulfate, and as a result of this reaction, ferrous sulfate is oxidized to ferric sulfate. This change, this transformation can be achieved with the help of acidified KMnO4, where occur the liberation of 5 nascent oxygen. Here only 1 nascent oxygen is consumed. Now, this acidified potassium permanganate oxidizes oxalic acid to carbon dioxide. Oxalic acid is a molecule with the molecular formula COOH twice, or this molecular formula can be simply represented as H2C2O4. This is oxalic acid molecule, and it captures on nascent oxygen. This hydrogen couples with the oxygen and just converted to the water molecule. There are 2 carbon dioxide molecules indicated by the formula part C2O4. So, this oxalic acid on oxidation just produces carbon dioxide and water, and acidified KMnO4 can oxidize oxalic acid to carbon dioxide and water. Now, this is the third reaction. This acidified KMnO4 oxidizes potassium iodide to iodine as per this equation. This is the balanced equation, and the completely balanced equation which is responsible for the transformation of potassium iodide to iodine. In this transformation, potassium iodide, you can see it is converted to iodine. The big numbers on left hand side and right hand side is due to the fact that in this expression, we are just avoiding the nascent oxygens. 5 nascent oxygen are produced by acidified KMnO4, and that nascent oxygen is consumed during the oxidation of potassium iodide to iodine. Whenever we are coupling all that oxidation part and reduction part, we will get to the completely balanced equation that is shown here. You need not to keep this equation in mind. This is for the sake of to understand how that transformation occurs. So, acidified potassium permanganate can convert to potassium iodide to iodine. During this transformation, potassium iodide consists of iodine in -1 state, and it is converted to I2. Here iodine is present in 0 oxidation state. So, -1 increased it to 0. This is oxidation. At the same time, KMnO4 is reduced to MnSO4. So, KMnO4 acts as the oxidizing agent, and potassium iodide acts as the reducing agent during the course of this reaction. Now, acidified KMnO4 oxidizes sulfite, that is SO3 2- sulfates. This is an equation showing that the transformation Na2SO3 can be seen in the left hand side of this reaction. Na2SO3 on reaction with the acidified KMnO4, because potassium permanganate and sulfuric acid are shown here. So, this is nothing but acidified KMnO4. So, sodium sulfite on oxidation with the acidified KMnO4 just converted to Na2SO4. Na2SO4 is sodium sulfate. So, sulfates are transformed to sulfate. Now, another reaction is acidified KMnO4 oxidizes halogen acids to halogen. You are familiar with the halogen acids like HCl, HBr, HF, etc. And this is a reaction which show the transformation of HCl, that is hydrogen chloride or hydrogen halide or hydrochloric acid, into halogen, and this HCl is oxidized to Cl2. So, here you need not add H2SO4 separately, because HCl as such acts as an acid. So, this reaction is the reaction between HCl and acidified KMnO4. Here HCl also an acid. So, you need not add H2SO4 separately. So, acidified KMnO4 oxidizes halogen acids to halogen. So, now we have to consider another important part of today's discussion, that is a real title of today's discussion, that is nothing but Permanganometry. So, from the discussion up to this point, we are familiar with the redox titrations and the potassium permanganate as an oxidizing agent. It is very well clear that potassium permanganate, especially in acid medium, is a powerful oxidizing agent. You can perform several volumetric analysis based on potassium permanganate as a titrant, and we are entering into the details. Such title is nothing but the Permanganometry. So, Permanganometry is a redox titration method that uses potassium permanganate as the titrant. It is one of the most common and convenient redox titrations due to strong oxidizing power of KMnO4 and its intense purple color, which act as a self-indicator. Whenever you are dealing with the permanganometric titrations, you need not add any indicator. That is, no external or internal indicator is required for titrations involving potassium permanganate. This is because potassium permanganate is associated with intense color and hence it is self-indicating. So, you need not add any indicator in permanganometric titrations. Now, KMnO4 acts as strong oxidizing agent on acidic medium. In neutral as well as basic medium, it is also oxidizing agent, but it is more powerful in acid medium. In permanganometric titrations, we have to standardize the KMnO4 titrant first. That is, in volumetric analysis, we must have a standard solution. So, we must have a solution with exactly known concentration. So, we have to standardize the KMnO4 solution first, because we should know the exact concentration of KMnO4 titrant to evaluate the concentration of another analyte. For the purpose of standardizing the potassium permanganate, we use a standard solution of oxalic acid or more salt. Remember, oxalic acid and more salt are primary standards. They can be directly weighed and converted to a standard solution. But remember, KMnO4 is not a primary standard. So, you have to prepare a solution of KMnO4 and it should be standardized first by using a standard solution of oxalic acid or more salt. So, that is the first part of the permanganometric titration. Now, generally, acid medium is preferred, and for providing the acid medium, we are using dilute sulfuric acid. During the reaction of KMnO4, manganese plus 7, as I already mentioned, is reduced to Mn2 plus. KMnO4 is self-indicating and the end point is generally the appearance of the pale pink color. Now we are discussing some selected permanganometric titrations. First of all, we are focusing on estimation of oxalic acid. Estimation means you are going to evaluate the exact concentration of a material. Here we are going to estimate oxalic acid with the help of permanganometric titrations. That is, our title is estimation of oxalic acid. This is our aim, to estimate or estimation of the mass of oxalic acid in the whole of the given solution, and you are provided with the n by 10, that is 0.1 normal solution of potassium permanganate and NLR more salt. These are the two materials you are having, and you have to evaluate the exact concentration of given oxalic acid solution. So, you are just entering into a chemistry laboratory. You are provided with 0.1 normal potassium permanganate solution, which is approximate only, and AR, NLR more salt crystals. By using these two crystals, you have to evaluate exact concentration of the given oxalic acid solution. Now, this is the principle. Potassium permanganate solution is standardized with a standard solution of more salt. What is meant by more salt? It is a double salt, which is a mixture of ferrous sulfate and ammonium sulfate. Here the water crystallization is 6. So, the exact molecular formula of more salt is, which is a primary standard also, the exact molecular formula is FeSO4, NH4 twice SO4, 6H2O. And you have to standardize the given KMnO4 solution with a standard solution of more salt. And this is the reaction which is responsible for the standardization reaction of acidified KMnO4. In acidified KMnO4, MnO4 minus ions are present. H plus indicates that the medium is acidic. So, Fe2 plus ions present in the more salt is quantitatively oxidized to Fe3 plus ions and no need for the indicator. So, you have to titrate a standard solution of more salt with a standard solution of more salt with the given potassium permanganate. That's why you can find out the exact concentration of the KMnO4. By utilizing that concentration, you have to again perform a titration with that KMnO4 and given oxalic acid. So, by using a standard solution of more salt, you have to standardize KMnO4 first, and then that KMnO4 is used to estimate the amount of oxalic acid. Standardized KMnO4 is titrated with the given oxalic acid solution. That is based on this reaction. KMnO4 plus 3H2SO4 simply indicate that it is an acidic medium, reacts with the oxalic acid molecule, and oxalic acid molecule is oxidized to carbon dioxide and water. So, this is about the procedure. First of all, you have to standardize the given KMnO4 solution by using a standard solution of more salt, and then that standardized KMnO4 is titrated with oxalic acid to estimate oxalic acid present in the given solution. So, these are various steps. This is for a consolidation. In the first step, you have to prepare a standard solution of more salt by weighing out some fixed quantity of oxalic acid and transferred it into a conical flask and then made it into a standard solution. And that standard more salt solution is used to standardize KMnO4. That is, standardization of KMnO4 is the second step. Here you are performing the titration between KMnO4 and more salt. In the third step, you are going to estimate oxalic acid, and that estimation is performed by using the standardized KMnO4, its titration with the oxalic acid. Now we are discussing second experiment, that is nothing but estimation of more salt. I already mentioned that more salt is ferrous sulfate, ammonia sulfate 6H2, and this is the aim of our experiment, estimation of the mass of more salt in the whole of the given solution of more salt, and N by 10 solution of KMnO4 and AR oxalic acid being provided with. So, you are entering into a laboratory, you are provided with a point on normal approximately KMnO4 solution and analar oxalic acid crystals, and you have to estimate the concentration of more salt present in the given solution. And this is the principle. Potassium permanganate solution is standardized with a standard solution of oxalic acid based on this reaction. Oxalic acid and KMnO4 in the acid medium produces or just oxidized oxalic acid to carbon dioxide and water. This equation is known to you, and that standardized KMnO4 is titrated with the more salt solution, which is based on this reaction, that is more salt in acidified KMnO4 or an acid medium is oxidized to ferric sulfate. So, here there are two kind of reactions. The first part is the standardization of given permanganate solution, which is through the titration of a standard solution of oxalic acid with the given KMnO4 solution. And in the second part, you have to do another titration, that is a titration between standardized KMnO4 and the more salt. So, these are various steps for the estimation of more salt. In the first step, you have to prepare a standard solution of oxalic acid. Oxalic acid is a primary standard, so you have to weigh out fixed quantity of oxalic acid and made up to the mark a standard solution. And using that standard solution, you have to standardize the KMnO4 by performing this titration, that is KMnO4 should be titrated with oxalic acid. So, now you standardize the KMnO4, and in the third step, using this standardized KMnO4, you can estimate more salt. Here you are performing a titration between the standardized KMnO4 and more salt. Now, equivalent weight calculations. We are now performing some equivalent weight and associated calculations. Equivalent weight or equivalent mass is a familiar concept to you. It is the mass of a substance that will react or displace a fixed quantity of another substance, such as 1.008 grams of hydrogen, 8 grams of oxygen, or 35.5 grams of chlorine. This is the definition of equivalent weight. Now we have to discuss the equivalent weight of oxidizing and reducing agents. The equivalent weight of an oxidizing agent or reducing agent is the mass of the substance that can gain or lose 1 mole of electrons during a redox reaction. Equivalent weight of an oxidizing agent or a reducing agent can be calculated by using this expression. equivalent weight equal to molar mass or molecular mass divided by number of electrons transferred per molecule of the reactant. The number of electrons transferred equal to total number of electrons gained, which is in the case of oxidizing agent, or total number of electrons lost in the case of reducing agent in a balanced redox equation. Now, equivalent weight of KMnO4 in acidic medium. You know the molar mass of potassium permanganate equal to 158 gram per mole, and MnO4 in acid medium just converted to Mn2 plus ions. It is a 5 electron transfer process. So, number of electrons transferred during this transformation is equal to 5, and it can be shown that the equivalent weight of KMnO4 in acidic medium equal to molar mass divided by number of electrons transferred, that is 158 divided by 5, and that is equal to 31.6 gram per equivalent. Now, equivalent weight of oxalic acid. Oxalic acid H2C2O4 is oxidized as per this equation. H2C2O4 or COOH twice plus oxygen gives 2CO2 plus water, and in this reaction 1 mole of oxalic acid is equivalent to 2 equivalents of oxygen, that is 16 gram of oxygen. So, it is clear that equivalent mass of oxalic acid should be equal to molecular weight divided by 2, and molecular weight of H2C2O4 dihydrate, which is exist as a dihydrate, oxalic acid dihydrate, equal to 126. So, its equivalent mass will be 126 by 2, that is equal to 63. These equivalent weight are very, very important as far as the calculations and some numerical problems or the laboratory titrations are concerned. Now, we are discussing equivalent weight of more salt. More salt, that is ferrous sulfate, ammonia sulfate 6H2 is oxidized as per this reaction. Ferrous sulfate present more salt is oxidized to ferric sulfate, and from this equation it is clear that 2 molecules of more salt reacts with 2 equivalents of oxygen, and hence the equivalent mass of more salt is same as its molar mass, and equivalent weight equal to molecular weight equal to 392. Thus, we concluded that in acidified medium, KMnO4 is having an equivalent weight of 31.6. In oxalic acid, in the reactions of oxalic acid, you can calculate the equivalent weight as 63, and for more salt, the equivalent weight equal to 392. Now, concept of autocatalysis. Autocatalysis refers to a reaction in which one of the product acts as a catalyst, accelerating the reaction as it proceeds. In permanganometric titration of oxidation, this phenomenon plays a significant role. Consider the titration of oxalic acid with potassium permanganate in acid medium, and this is the reaction which indicates the reaction between acidified KMnO4 and oxalic acid, and as a result of this reaction, MnO4, potassium permanganate, is converted to MnSO4, that is manganese sulfate. At the same time, oxalic acid is oxidized to carbon dioxide and water. This reaction is familiar to you, and with respect to this reaction, we are illustrating the concept of autocatalysis. This reaction is slow initially. You should note, whenever you are just starting the titration between acidified KMnO4 and oxalic acid, the reaction will be very slow initially, but as the reaction proceeds, the rate of the reaction, the speed of the reaction, the decolorization of KMnO4 will be very fast. What is the reason for this reaction? The answer is here, it is nothing but autocatalysis. This reaction will be fast after some time. This is because of the fact that one of the product, MnSO4, that is manganese sulfate, acts as a catalyst for the future reaction. In the previous slide, I just show you that one product is MnSO4, and initially MnSO4 is not produced. After some time, some quantity of MnSO4 is produced in the reaction medium, and that MnSO4 acts as a catalyst for the future reaction. That is why there occur a high speed after some time. This phenomena is termed as the autocatalysis, or the thing, one of the product acts as a catalyst for the future reaction. That phenomena is known as, that peculiarity is known as the autocatalysis. Now we can have some numericals based on the concept we have learned. First of all, how many grams of oxalic acid dihydride, that is H2C2 for 2H2, are needed to prepare 100 ml of a 0.5 normal solution? As far as the volumetric analysis is concerned, weight calculation is very, very important. You can calculate the weight of the substance required to prepare a particular solution, a fixed concentration of a solution, by using the expression weight required equal to VEN divided by 1000, where V represents the required volume, E represents the equivalent weight, and N represents the normality of the required solution. Now, in the present problem, we can have the mass of the substance required equal to the amount of the substance of amount of oxalic acid required equal to 100, that is the volume you have to prepare 100 ml of the solution. 63 is the equivalent weight of oxalic acid, and 0.5 normal is the concentration of the solution. And so, on substituting in the expression Vn divided by 1000, you will get 3.15 gram. That is 3.15 gram of oxalic acid when dissolved in 100 ml of water, you will get a 0.5 normal solution. Moving on to next problem. Find the weight of more salt required to prepare 0.1 normal 250 ml solution. Here also you can use the expression weight required equal to Vn divided by 1000. Here also V represents the volume in ml, N normality, E is the equivalent weight. On substituting various values here, you will get the weight required equal to 250 into 392 into 0.1 divided by 1000, that is equal to 9.8 gram. That is 9.8 gram of more salt when put it in 250 ml of water, you will get a 0.1 normal solution. Now another problem. In a titration with the standard oxalic acid in acid medium, the concentration of a solution of KMnO4 is obtained as 0.45 normal. What is the weight per liter of KMnO4 solution? Weight per liter can be calculated by using an expression. Weight per liter is equal to normality into equivalent weight. So, in this problem, you have to find out the normality first. Normality just multiplied with equivalent weight, you will get the weight per liter. Normality is given in the problem as such as 0.45 normal. You know the equivalent weight of potassium permanganate as 31.6. So, you have to multiply 0.45 with the 31.6. You will get the value 14.22. That is the weight per liter. Now, an MCQ based on the concept. The volume of 0.1 normal oxalic acid required to neutralize a 20 ml solution of 0.125 normal KMnO4 in acid medium is. These are the options. Option A 20 ml, option B 25 ml, option C 10 ml, and option D 12.5 ml. How to calculate the volume of 0.1 normal oxalic acid required to neutralize 20 ml of 0.125 normal KMnO4. A very familiar equation from volumetric analysis is with you, that is N1 V1 equal to N2 V2. So, you have to take oxalic acid first, its concentration is 0.1, its volume is to be calculated, let it be taken as V1, that is equal to N2. N2 means 0.125, that is the concentration of KMnO4, and the volume of KMnO4, that is equal to 20, and you can calculate V1 as 0.125 into 20 divided by 0.1. So, you are getting answer B, that is this value should be equal to 25. Your option will be option B, 25 ml. Now, this is the last problem. 3.92 gram of more salt is dissolved in 250 ml of water to get a solution. The normality of the solution will be. These are the options. Option A 0.04 normal, option B 4 normal, option C 0.5 normal, and option D 5.3 normal. You have to calculate the normality. Normality of a solution is given by the equation weight per liter divided by equivalent weight. 3.92 gram of more salt is dissolved in 250 ml water. So, 3.92 divided by 3.92 gram of oxalic acid is dissolved in 250 ml water only. So, divided by 250, that means in 250 ml you are having 3.92 gram. Then what will be the weight per liter? In order to get the weight per liter, liter means 1000 ml, you have to just multiply with the 1000. This is the weight per liter. This weight per liter divided with the equivalent weight. Equivalent weight of more salt is equal to 392. On simplification, you will get to the final answer as option A that is 0.04 normal. That is, normality can be calculated by using the expression weight per liter divided by equivalent weight. That all about the present module on permanganometry. Have a nice learning experience. Thank you.